let us continue. Remember, we were dealing with an abstract differentiable manifold. We choose one point, call it P. Then we consider the algebra of function germs on the manifold about that point P. We call it f of P. And then we consider the set of directional derivatives on that algebra of function germs about the point P. So all of this is really associated to a particular point P here. All of this happens on an abstract differentiable manifold. And we found that in order to make these objects workable, we need images of them, concrete images of them, where we can deal with the images then. We notice that we obtain concrete images or representations of these objects on Rn by using a chart. Using a chart, we obtain that every point on the manifold, I'm here pretending that the chart covers all of the manifold. In practice, we may need several charts to cover the manifold, but that's not important for now. So using a chart, every abstract point on the manifold has an image in Rn, and therefore n numbers associated with it. We therefore have a continuous way of labeling all the points of the manifold. Similarly, we obtain that every function germ about the point Q gets mapped through the chart into a function germ about the point P in the abstract manifold. So while every point P has an image in Rn, every function germ f has a pre-image in the function germs about Q. And how does that work? It works by pre-composition. A function germ on this side, a function germ that takes as input these points, gets mapped into a function germ on that side, which accepts as input points in here, simply by pre-composition. You take a function that lives on here and pre-compose it with the chart, and that makes it a function that lives on here, that takes as input points here. So this map between function germs here and function germs there is an algebra homomorphism, phi star, and it is the precomposition of the chart and the function germ G. Take a function germ G, precompose the phi, you get a function germ F. Notice that the arrow has a reverse direction now. Similarly, if we have a directional derivative here that feeds us on the inputs from here, then that can be mapped into a directional derivative over there that feeds on inputs in those function germs, namely again by precomposition. You take a directional derivative here. In principle, it accepts inputs from here, but by prepending that map, it accepts inputs from there. Therefore, it becomes a directional derivative in here, because it accepts inputs from there. So you see the arrow is reversed again, and this tangent map is now mapping in this direction. Whenever you have such a construction, it doesn't have to be charts and algebra homomorphisms or tangent maps. Whenever you have such a composition, a precomposition law, and you can call this a pullback. So this would be the original map, that would be its pullback. That would be an original map, and that would be its pullback. And if you step over one, then the arrows point in the same direction. You could call that push forward. So phi star is the pullback of phi, and TP phi is the pullback of phi star. So now we have that, and I already said that when I showed you the picture, we have that every point P has a concrete image in Rn. Every function germ here has a concrete pre-image in the function germs on Rn. And every tangent vector here, every directional derivative here, has an image, a concrete image, in Rn. I mean, in the tangent space to a point in Rn. And we, with great effort, were able to prove that every tangent vector here over a point in Rn takes a particular form. We define the tangent vector as a linear map that obeys the Leibniz rule. And on those grounds alone, we were able to show that every tangent vector is a linear combination of partial derivatives, is therefore a directional derivative. Right? Remember, that was an amazing thing that just linearity and the Leibniz rule determined that everything that does that, everything that's linear and obeys the Leibniz rule, is a directional derivative, is a linear combination of the partial derivatives. And that's very useful. Now, since that is assumed to be an invertible differentiable map, a diffeomorphism, this is going to be invertible, that's going to be invertible. So we have a one-to-one correspondence between things that we can explicitly write down as linear combinations of partial derivatives and something that's more abstract. So we have a nice image of those things. We can handle them concretely. That's what this slide is saying. So every point in the manifold has now a concrete image. Every point in the tangent space to the point P in the manifold has now a concrete image in the tangent space to its image, Q, on the manifold. So this is a tangent vector in the abstract manifold. That is a tangent vector to a point in Rn. And we calculated with much effort that every tangent vector to a point in Rn takes this particular form. Eta is a linear combination with some weight factors times the partial derivatives. It's a directional derivative. So then the next question is, of course, given a point P in the manifold and a tangent vector to it, so here's the manifold, here's the point P, and let's say we have a tangent vector there, then what if we have two charts? What if we have two coordinate systems? Then how do those coefficients, these ones, change under change of coordinate system, under change of chart? So here's the abstract picture for that. Here's the manifold. And here are two more manifolds, Rn and another copy of Rn. And we have charts. One chart that we may call beta, and another chart, it's another diffeomorphism into Rn called alpha. Both provide coordinate systems. The same point on a differentiable manifold is now mapped onto a point in Rn here, and in general, some completely different point in Rn over there. Which means that the same point has one set of n numbers as coordinates, but also another set of n numbers as coordinates. Overall, we have a diffeomorphism from this copy of Rn into that copy of Rn simply by running that diffeomorphism backwards and then running that diffeomorphism forwards. Let's call this big one phi. Phi is mapping alpha inverse, gets us this way, and then afterwards beta. So this little circle means concatenation. So first alpha inverse, then beta. That's the diffeomorphism as well, this map over here. Now this is a diffeomorphism though from Rn into Rn. So we know how to handle this one. This is given by explicit functions. We are mapping explicit coordinates explicit variables x1 to xn into explicit variables x tilde 1 to x tilde n. Now when we do this change of chart, then we get this big picture here. That's just a picture that I had up. And now we add to that the function germs about the point Q, and the function germs about the point P, function germs about the point S. Now this chart alpha has a pullback map, alpha star, going in the opposite direction, which maps function germs here into function germs there. And similarly, the function germs here get mapped with a pullback beta star into function germs about the point P here. And again, by concatenating those pullbacks, we get one big pullback that gets us from function germs over this copy of Rn to function germs over that copy of Rn. And that's the map phi star. After all, these two are just differentiable manifolds. So we can use the same machinery as we had before to consider maps directly, diffeomorphisms directly from here to there. In this case, it's the phi, and its pullback is directly the phi star. And you can also show that this is just a concatenation of the two pullbacks, the individual ones.
What tells you that any chart you pick at P will be diffeomorphic to Rn and not Rm, some different dimension?
The constancy of the dimension, that's a messy thing. I mean, let's not go into that. It would be a longer thing. I'm trying to avoid proofs like that. Yes. But remember, it was part of the definition of what a manifold is, that the charts map into Rn, and then you would have to have transition maps that are invertible, and they could not possibly be invertible if the dimensions differed between two charts, and the chart change map could not be invertible if that were the case. But it's tedious, to work that out in detail. But ultimately, that's the reason. Okay, so this is for the function germs. And then again, we have directional derivatives. We have tangent vectors that act on the function germs. Remember, a tangent vector is a derivation on that algebra. It's a linear map that obeys the Leibniz rule. And it feeds on those elements, on function germs, and it outputs a number, the directional derivative of the function germ at that point. Okay, so we have then, again, pullbacks to those maps that just reverse the arrows, and we have an overall pullback from that Rn to that Rn, from that tangent space there to this tangent space over here. And this last part is what we're interested in. So here we have this provides us an image of an abstract tangent vector with respect to the chart alpha. Here, we are provided another image of an abstract tangent vector with respect to chart beta. And the question is, how are those two images related? How are those two tangent vectors related? How are those two images of a fixed tangent vector related? How are those coefficients related? Of course, you all know how that goes, but let's go through the formalisms as an exercise.
Just to make sure I have the terminology right, so phi star is the pullback of phi.
That's right.
And then the final map is the push forward of
phi. Of phi, that's correct. Right. Yes. But it's the pullback of the phi star. Right. That's right. So now every point P has two images. Every abstract point P on the manifold has two images. It has an image with respect to one chart, and these are those coordinates. And it has an image with respect to the other chart, and then that's the chart beta, and then it has these coordinates, those n numbers of Rn, denoting a point in Rn, specify that image. The overall map phi, which goes all the way from one chart to the other chart, is mapping those n coordinates into those n coordinates, because after all, this is just a function from Rn to Rn. We can even write it more concretely. We can write the tilde variables. Each one of the tilde variables is a function phi I of the untilde variables. This is a completely explicit function, concretely. If you have a specific example in mind, these will be regular ordinary functions from Rn into Rn. In particular, we can differentiate them, for example, if we need to. Okay, so every point has two images. Every abstract point on the manifold has two images. Every function germ on the abstract manifold, every f in fp of m in the algebra of function germs, has two pre-images. So it's the image of 2 points. Namely G in the algebra of function germs about Q, and H in the algebra of function germs about S. And we have, and this is because of the way everything is constructed by precomposition, we have that a function germ at a particular point P, this is the one pre-image, is the same as is the same value as the value of the function germ at the point Q on the abstract manifold. Is the same as the value of the function germ H on the point S in Rn. That's because of precomposition. This is how it's defined. And similarly, a function in one representation, in one chart, h of x tilde, gives us the exact same output as the image function on the coordinates on these x. This is what you would expect a scalar function to do from your previous knowledge of GR. Scalar functions don't transform under coordinate transformations, and here we see that ultimately the reason is that those function germs, the pullback for function germs is defined by precomposition. That's why they don't change in a neighborhood, right? They have to be, we're talking here about function germs, so their equivalence classes, all of that holds on some neighborhood of the points in question. Now, every tangent vector to an abstract point of the abstract manifold also has two images now. One image eta with respect to one coordinate system and one image nu, a tangent vector with respect to the other coordinate system. And by construction again, because of the precomposition business, we have that when you apply the abstract tangent vector onto an abstract function germ, then you get a certain number out of it, which might be 5.7 or something, and you get the same 5.7 if you apply the image of the tangent vector under a chart to the image of the function germ. And if you do it in another chart, same deal, you get the same 5.7. Okay? That's because of the precomposition. That's important. That makes it a representation. Everything that happens on the abstract manifold happens exactly the same with the same output on the two charts. Now let us look at this explicitly. Let us spell it out what that means. Now we can't make psi of f itself explicit. It doesn't have coordinates itself. It's imaged onto coordinate systems. So let us consider the equation eta of g equal to nu of h. So we take the two far ends of the graph and relate them to each other. So we have eta of g. This is all happening in Rn. We know, therefore, that eta, a tangent vector, is a linear combination of the partial derivatives. Here it is. It's some linear combination of the partial derivatives. That's eta. And it's acting on a function germ. Here it is. That's our function. It's a representative out of that germ. And those derivatives are to be evaluated at the point in question, and that is the point Q. Here, everything in a different coordinate system. On the right-hand side coordinate system, nu of h. Nu, a tangent vector, we know again by the lengthy proof that we did last time, we know that nu is a partial derivative. It is some linear combination of the d by dx tildes. When we apply it to the image of the function germ h, then this is how it looks like. Directional derivative acting on that function. And then evaluating those derivatives at the point in question. Now remember that the output of the functions is the same in each coordinate system. If you're looking at imaged points, points that correspond to each other, and functions that correspond to each other, then the output is the same. That's what we denoted with this red star. So we can write h of the x tildes also as g of the x. But then this is a partial derivative on the x tildes. In order to make it act on the x's, we have to use the chain rule. So we just carry all of this forward, the new coefficients, and then those partial derivatives with respect to x tilde by the chain rule are the same as dx by dx tilde, d by dx. So what we have is this equation. That is equal to this. But notice that this has to be true for all function germs g. And that implies that this equation, this equal to that, has to be true even when you drop the g. Just for the abstract differential operators, it also has to be true. So we have that this tangent vector has to be the same as that tangent vector. So those coefficients are these coefficients. Because partial derivatives are linearly independent, this must be true for every coefficient in front of the partial derivatives. Okay, so we have that the eta I coefficients are related to the new j coefficients through this Jacobian matrix here. It's the Jacobian matrix of the change of chart. Remember phi, the map that implements the full change of chart, going all the way from one side of the picture to the other side of the picture. That is the tangent map to that. This is the Jacobian matrix to that big map. So the big diffeomorphism, the change of coordinates diffeomorphism. And conversely, if you want to express the new coefficients, the coefficients of the tangent vector in the in its chart in terms of the coefficients in the other chart, then we just have to invert that matrix. And that is generally an invertible matrix, as one can show, because the diffeomorphism is assumed to be invertible. Okay, all of this should look familiar, maybe not in that language, but you know the content of it. So for a summary, abstract manifold, two charts. Overall, there's a big diffeomorphism phi that gets us from one chart to the other. And given one tangent vector to this abstract point here, this tangent vector has a representation or an image over here and an image over there. Over here, it's an image which is a directional derivative with certain weight factors and in front of the partial derivatives, and here other weight factors in front of the partial derivatives, namely eta is equal to eta I d by dxi on that side. And on this side, the image is nu I d by dx tilde I. And these coefficients are related to each other. And the relationship is simply so that Jacobian matrix here. That Jacobian matrix can also be written using the phi I functions. Remember the x, the new variables x can be, the new variables x tilde can be expressed in terms of the old variables xi in this way. The x tilde I are phi I of these. This is the change of coordinates map. And that Jacobian matrix is also simply this. Okay, so we know now how the weight factors change when we change chart for these tangent vectors. This leads us to the physicist's definition of tangent spaces. Remember, we started with the algebraic definition of what a tangent space is. A tangent vector, according to the algebraic definition, is the linear map on function germs to the from function germs to the real numbers, which obeys the Leibniz rule. According to the physicist's definition, a tangent space is defined slightly differently, but equivalently. Namely, a tangent vector, psi physical, I'm using here superscript to indicate for the moment that it's according to another definition. A tangent vector, according to the physicist's definition, is a map that assigns to each germ of a chart. Let's just say chart. You know, charts really are global things, but what matters if we work point-wise is only the germ of a chart, actually. So a tangent vector is a map that assigns to each chart a coefficient vector Rn, like those phi n or those phi mu or those eta mu, so that if these are the coefficients with respect to one chart alpha and nu are the coefficients with respect to another chart beta, then they have to be related by this map. So that's probably how you first encountered tangent vectors, as defined as coefficients that transform according to that rule. And this is also how Einstein understood what a tangent vector is. Okay, so far we have then two equivalent definitions of a tangent space. Algebraically, we have that a tangent vector is defined through the following property. It's a linear map which obeys the Leibniz rule. And it turns out, as one can prove, all linear maps to the real numbers which obey the Leibniz rule, take that form. And then there is the physical definition, which is saying that a tangent vector is not a map. The tangent vector is not a linear map that obeys the Leibniz rule, but instead it associates to every chart. It's a linear map that associates to every chart a bunch of numbers in such a way that under chart change, you get a Jacobian matrix involved. Okay. Now, finally, the third and last definition of what the tangent vector is. We will need this one as well. And that definition will also give us a somewhat deeper insight into why it is that the algebraic definition succeeds. So this should be very intuitive. The idea is that the tangent vectors are actual tangents to paths. Consider a path in the manifold. So this is our manifold. Here's the point P. And let's say this line here is a path. A path is defined as a map from R into the manifold. Think of this as the time axis. And then we require that as the time reaches the value 0, our path goes through the point P. Okay, so this is early times, and then this is late times. At time equals 0, the path is at the point P. Of course, we assume all of those paths to be smooth. Then we notice that whenever we consider a scalar function on the manifold, so a map from the manifold into the real numbers, such as a temperature distribution, let's say, then we can concatenate the path with this temperature distribution. So we first have the path, and then we apply the temperature distribution, which is to say you travel along the manifold while recording the temperature as a function of time. This is a map from R to R. The time in, the temperature out. Let's use that. We define two paths to be equivalent, two differentiable paths we call equivalent if for all temperature distributions, let's say, if for all temperature distributions, the rate of change of temperature as you pass through the point P at t equals 0 is the same. So if you have one path and you travel through this path, and as you go through the point P, the change in temperature is a particular value, and you take another path, and you go through the point P, and the change of temperature is the same value as before, and if that's true for all temperature distributions, then we say that these two paths are the same. Not the same, they're equivalent for our purposes. Really what it means is only that those two paths have the same slope, the same tangent at the point P. Before and after, they may differ, but they have to have the same tangent if that's supposed to be true, if that's true. So the intuition is that two paths, gamma A and gamma B, according to this definition, are equivalent if they have the same velocity at P. Otherwise, you could find a temperature distribution where that equality would not hold. And then the geometric definition of the tangent space is the set of equivalence classes of such paths. So all paths that are equivalent with respect to this definition constitute one tangent vector. Let's see, is that definition, the geometric definition of the tangent space, and the algebraic definition of the tangent space equivalent? Later on we will not use those superscripts anymore. We will just write Tp of m, understanding that all the three are equivalent. But let's convince ourselves that they are equivalent. So they really are equivalent, and here's how we see that. Each path gamma actually defines a linear map in the sense of the algebraic definition of what a tangent vector is. Namely, take a path, gamma. How is that a linear map that obeys the Leibniz rule? A linear map on functions that obeys the Leibniz rule. That's what we have to show. So gamma is a path, and therefore belongs to an equivalence class of path. Therefore, it is a tangent vector. So every smooth path, gamma is a tangent vector according to the geometric definition. We want to see whether it's also tangent vector with regards to the algebraic definition, which means it's got to map functions into real numbers in a linear fashion, obeying the Leibniz rule. Let's see. We define the linear map from the algebra of function germs into the real numbers in the following way. You take your path, you take your function germ, and then you use it as a temperature distribution in the previous sense. You use it as a thing to be precomposed with the path. So you have the path, then the temperature distribution, then you take the time derivative of it, and you evaluate what that is at that point. That gives you a real number for every function that you plug in, for every temperature distribution that you plug in. And it's easy to show that this map from function germs into real numbers is not just linear. Well, it's clearly linear because of the derivative is just linear, but it also obeys Leibniz rule, and that's again because that's a derivative. You just have to spell it out explicitly that the Leibniz rule holds. This is here spelled out. Let's not go into all the details. It's fairly obvious. So the Leibniz rule is inherited from the Leibniz rule of the d by dt. So what we see is that the geometric definition and the algebraic definition of tangent spaces is equivalent. Because, actually I showed it only one direction here. I showed that geometrically defined tangent vectors can be viewed as linear maps from function germs into real numbers that obey the Leibniz rule, and therefore they are also algebraically defined tangent vectors. The reverse also would need to be shown, but it's just a bit of tedious writing down stuff. It's not difficult. Okay, any questions so far? Because this was completing now the business with the tangent spaces. So we have three definitions and they're equivalent, because we showed that the algebraic definition is equivalent to both the physicists and to the geometric definition.
Just a quick question.
Okay.
So your bar over the gamma is, I think that's what the push forward is in differential geometry. If I remember correctly. Is that?
No. So here it just means that the equivalence class of path is now interpreted as a map from the function germs into the real number.
Because we, in diffgeo, we have like a gamma lower star, and it's f, and it's
well,
the derivation of f of gamma.
Well, remember that this is a precomposition.
Yeah.
Therefore, you can always view this as a pullback.
Okay.
Okay, so.
I have a question.
Yep.
You mentioned that the algebraic definition has the advantage in generalizations, such as in non-commutative geometry. So for the other two definitions, are there other advantages?
I would say so. The physicist definition is advantageous because it's practical. It's easy to check whether or not a certain transformation rule is applicable. The geometric definition is useful because it's intuitive. And especially when in GR we consider paths of observers, poor souls falling into a black hole or something like that, then it's nice to know that tangent vectors can be viewed as actual tangents to path. But the equivalence that we talk about here goes out of the window when you go to non-commutative geometry, where there are no paths. Just like there are no paths on quantum mechanical phase space, because quantum mechanical phase space doesn't have points. You can't localize to arbitrary accuracy in phase space. But you can always check for derivations on an algebra. Derivations on an algebra being maps that are linear and obey the Leibniz rule. It doesn't have to assume that the algebra is commutative. In fact, later on in this course, we will encounter derivations that act on algebras that are not commutative, such as the exterior algebra. It's not even in commutative geometry, it just comes up in ordinary differential geometry already. Okay, so the cotangent space TP of M star. Sometimes maybe I put the star over there. I'm not sure if I'm consistent with where I place the stars. Now, the definition here is this. It's basically the dual space to the tangent space. Now, just to make sure we are all on the same page about dual spaces, let me review that. Actually, I remember when I was an undergrad and I first learned what the dual space to a vector space is. I really loved that. I mean, it was really liberating to see how a feature of math is at work, which is absolutely crucial. Remember that in math, when you have a set of axioms, let's say the axioms for a vector space, or the axioms for an algebra, then literally anything that obeys those axioms is given that name. Anything that involves the axiom that obeys the axioms of an algebra is an algebra. I mean, let's say the axiom of an associative algebra is an associative algebra. Everything that obeys the axioms of a vector space is called a vector space. In fact, there's a book by Gilmore on group theory where he makes the point of constructing something that involves a bunch of bananas. And then he shows that it obeys certain axioms. He said, well, okay, it involves a bunch of bananas, but it obeys the axioms. Therefore, let's call it whatever you wanted to call it. Right? So it's very nice to see this because this can be done recursively. And this is what's happening in linear algebra here. Given an n-dimensional vector space V, the set of linear maps from the vector space into the real numbers actually obeys the axioms of a vector space. Because you can add any two such linear maps, you can multiply them with 7 and they're still linear maps from the vector space into R, and that's already all you need to have the vector space axioms obeyed. And that vector space is called the dual space. So the dual vector space to a given finite dimensional vector space, for infinite dimensions there are different versions of dual. For finite dimensional vector space, the dual vector space is uniquely simply the set of linear maps from the original vector space into the real numbers. And we denote that with V star. So the dual vector space to the tangent space at a point P is called the cotangent space, and we denote it with TPM star. Still, everything is very local. Everything is, we're talking about the tangent space to one particular point and the cotangent space there. Now we notice that for every germ of a function at point P, for every such function, we obtain naturally, automatically, an element of the dual vector space. Right? I mean, you may be wondering, how do we populate that dual vector space? What's in there? How can we get dual vectors? How can we get cotangent vectors? What are examples of cotangent vectors? And what I'm claiming now is that take any function, or really function germ, so a function is a representative of a function germ, take any function, and I mean, differentiable function, of course, we are always dealing with smooth functions now. Take any function, and then you can use it to obtain a cotangent vector at our point. How do you do that? Well, first of all, how is it called? It will be called df. df is the cotangent vector associated to an arbitrary function f. So it's an element of TPM star. This will be the d for differentials for the exterior derivative. That thing will play a big role in this course. You can actually view it as a map from the functions into the cotangent space. So df is what cotangent vector? df, the differential of f, is defined to be the linear map which takes a tangent vector and maps it into a real number by taking the tangent vector and, remember it's a directional derivative, and have it act on the function. That's all. That's a linear map. So you take a function and you feed it to the tangent vector. That will, as output, give you a real number, namely the directional derivative of the function at that point. And since it's a linear map, it's an element of the cotangent space. Right? You feed it a tangent vector, and you get out a number. Which number? Well, the number that you get when you apply the tangent vector to the function. Okay, so keep in mind df, the differential of a function. You may have seen that before in thermodynamics or perhaps in the first course on GR. And you may have been told that it has to do with infinitesimals and so on. It has nothing to do with infinitesimals, really. Really what it is, it's a map that takes an abstract function or just any function and maps it into a cotangent vector. And the cotangent vector that you obtain is this. Sorry, I'm repeating myself, but it's so important. Can't lose you here at that point. Okay, so the df is a cotangent vector, which means it's a linear map on the tangent vectors. It maps tangent vectors into real numbers. And it does it by taking a tangent vector and mapping it into the real number, which is the directional derivative of the function f that you obtain by using psi. Okay, so I wrote here that a D can therefore be viewed as a map from the function germs into the cotangent space. That's just a hint of something that will come up later. How does that look like concretely in a coordinate system, that is in a chart? Well, then in a chart, we have that the abstract tangent vector to a point P, an abstract tangent vector to a point P, has an image in a coordinate system, which we may call eta, where eta is the tangent vector to a point Q in Rn. So let's check how that thing is acting, or how that thing is being acted upon by a cotangent vector. So we take a function g in the a function g on the manifold, and then dg is a dual vector, and it must map a tangent vector into the real numbers in a linear fashion. How does it do that? Everything is done in a representation. So the differential, the cotangent vector associated to a function g is mapping a tangent vector into this number here, namely the tangent vector acting on the function, which is to calculate the directional derivative at the point, that's the number. And explicitly, it's this. It's the tangent vector, eta, and the partial derivatives acting on the function in question, evaluated at a point. That is a linear map. And it's a linear map because if you fed 5 times eta, you would get 5 times the output, because the 5 would be here. If you had this cotangent vector act on 2 tangent vectors, eta 1 plus eta 2, then that would be additive here as well. So it's linear. Therefore, dg is an element of the cotangent space. So since all of the tangent vectors, as we showed in this lengthy proof on Friday, take this particular form, they are all directional derivatives. I mean, we defined them algebraically. Now we can see it also in different ways. They're all directional derivatives. We have that a basis in the space of tangent vectors is given by the d by dxi. You see, they are linearly independent. It's not the case that 2 times d by dx1 plus 3 times d by dx2 is d by dx3 or anything like that. They are linearly independent. So you can view the partial derivatives as a basis in the tangent space. Yeah?
Are you saying that cotangent space is isomorphic to the space of function germs I have found?
No.
No. They're just like, is it one-to-one though? Or like,
No, the space of function germs is much larger. It's an algebra. Remember, there's an algebra of function germs, and an associative algebra is also a vector space, but it's an infinite dimensional vector space. Whereas our tangent and cotangent spaces are finite dimensional.
right. Okay.
Mm-hmm. Okay, so for example, with the smooth functions, you can give that many derivatives at a point and specify function germs in this way. Okay. Okay, so we have a basis in the tangent space. For example, the partial derivatives are directional derivatives, and they do form a basis in the tangent space. I mean, you see, I'm not doing the pure mathy thing of proving this now, but it's pretty clear that, I mean, they're linearly independent and that they are complete is because there are n of them and it's an n-dimensional space. Now, we haven't shown it's n-dimensional, but it was part of the definition of the diffeomorphisms that they are invertible, and that guarantees that the dimensions are the same. So a basis in the tangent space is given by the partial derivatives. What then is the dual basis in the cotangent space? Every basis in a vector space has a dual basis in the dual vector space. And the dual basis is such that if you evaluate the dual basis vector on the original basis vector, then you get 1, and evaluate it on the other basis vectors, you get 0. So what is the dual basis in the cotangent space? Well, consider the coordinate functions. What are the coordinate functions? Well, there are n of them. The coordinate functions map Rn. Remember, we are working in a chart here. The coordinate functions map points in Rn to R. And what value do they give? Well, the xk coordinate function is a function that maps all points in Rn into the value of the kth coordinate. It's literally the function f of x equal x superscript k. This is not to the power of k, right? It's a superscript. It labels which coordinate it is. So let's consider those coordinate functions. They are legal functions, just like sine, cosine, and any other function is. And it's smooth too. It really ought to give us, using the d, a cotangent vector, each one of those. Let's look at those cotangent vectors, the d, xk. We considered the df before, where f was an arbitrary function. Now we consider the d xk, the differential of xk, of the kth coordinate function. This is an element of the cotangent space. What does it do? Well, every vector of the cotangent space has the same job. It has to map tangent vectors into real numbers in a linear fashion. That's what dual vectors do. Mapping the original vectors into real numbers in a linear fashion. And how do they do it? Well, the differential of the coordinate functions are mapping the basis vectors of the, they're mapping every tangent vector into a real number. In particular, we can feed it basis vectors in the tangent space. These are particular basis vectors, and they are mapped into whatever the outcome is of having that tangent vector act on the function xk. And that is the tangent vector acting on the function xk, which is delta ik. Therefore, we found the dual basis. The dxk form a basis in the cotangent space, and it is the dual basis because when applied to the original basis of the tangent space, to the basis of the tangent space, it just gives us this outcome. Notice that this has nothing to do with the metric of general relativity or the metric on any differentiable manifold, because we don't have a metric here. A metric allows you to get a real number out of two tangent vectors. This is a real number out of a tangent and a cotangent vector. Very different. This knows nothing about distances on the manifold. Okay, so we have now a basis for the tangent space, the d by dxi, and we have a basis for the cotangent space. These are the differentials of the coordinate functions dxk. So you see they're not infinitesimals of anything, they are linear maps that map tangent vectors into real numbers in a linear fashion. Okay, so here we have a basis of the cotangent space. So we have, since we have a basis now, and we know it's n-dimensional, the dimension of the dual vector space is always the same as the dimension of the original vector space, except if that dimension is infinite, then they may not be of the same infinite cardinality. So every element of the cotangent space has to be a linear combination of basis vectors. Now, we identified those guys as basis vectors. Therefore, every element of the cotangent space is some linear combination of those basis vectors. Can be written as sum over I from 1 to n, omega I dxi. So even if we take an arbitrary function f, consider its differential df, it's got to be possible to write it in this form. Because it's a cotangent vector, and every cotangent vector has that form. It's a linear combination of the basis vectors. Now let's see, what's the action of a general cotangent vector? Well, a general cotangent vector, linear combination like this, is mapping arbitrary tangent vectors into real numbers. How does it do it? Well, you feed it an arbitrary tangent vector like this, and omega maps it into whatever number comes out when you apply omega to this. So you apply omega to the tangent vector, but that is whatever number comes out when you apply the tangent vector onto the functions that are involved in the definition of the omega. So we have this derivative here acting on the xi. These were the functions that defined the differentials. So we have, if we just organize our sums a little bit better, we have the sum over all the I, the sum over all the j, the coefficients omega I, and the coefficients eta j. And then we have these acting on the coordinate functions, but that is the delta ij. So the sums simplify, we're left with just one sum, and it's this. So what we see is that when you express a cotangent vector omega in the dual basis, and you express a tangent vector in its basis of partial derivatives, then the evaluation of a cotangent vector on a tangent vector is simply the sum of the product of the coefficients. This is why it is useful to use the dual basis. Generally, later in the term, we will allow ourselves to use arbitrary bases in the tangent space, arbitrary bases in the cotangent space. In this way, we can view general relativity as a gauge theory. But it will generally be convenient to use whatever basis we choose for the tangent space, to use the dual basis for the cotangent space. Things just get messy. And so it's easy to keep them dual to each other. So now in particular, if g is an arbitrary function, smooth function, then its differential, which is an element of the cotangent space, must be of that form, right? Because it's a cotangent vector. And all cotangent vectors take that form with suitable coefficients omega k. But what are those coefficients?
Right now in the course, are we being careful with where indices go, upper or lower? And
yes, it does make a difference whether they are upper or lower.
If you go up a slide, I think you have delta ij. Like most part, I think delta ij has no.
Where? Oh yes. Oh, sorry. Yes, I got to fix that. Yeah.
Yeah. Sure.
Yes. I mean, for the Actually, for the Kronecker delta, that's the only thing where it doesn't matter. But yes, it would be better to. Yes, yes. I should have that the I is an upper index. That's right.
Are we going to use Einstein notation?
Yes, we are. Yes. Still not, but yeah, soon we will drop the summation symbols, of course. It would be too tedious to drag it along all the time. Okay, so consider now an arbitrary function and its differential. Well, the differential is a cotangent vector. As a cotangent vector, it's got to be a linear combination of the basis vectors, which are given by the differentials of the coordinate functions. So there must be some omega k. Let's calculate the values of the omega k for a given function g. We can do it this way. So we have the differential of g acts on a tangent vector in this way that the eta, the directional derivative acts on the function, right? This was the basic way in which differentials work. The differential of a function, is a cotangent vector. It maps the tangent vector into a real number by letting the tangent vector act on the function. Therefore, evaluate the directional derivative at a point, giving us a number, right? This is how you get to the differential of a function. This is when you spell it out, you have here the eta. This is the eta acting on our function g. Okay, this is equation 2. Let's compare that. You see, here we have summation of eta I, and then some bunch of stuff here. Let's compare that with our equation 1 up here. You have a differential, you have a cotangent vector acting on a tangent vector. It's this, where these are the coefficients of our cotangent vector in the dual basis. So the omega I times eta I. Down here, we have the action of the cotangent vector on this gives us that. These must be the coefficients omega I in the dual basis. The omega I are these, which is to say that the differential of a function is given by the partial derivatives of that function times the differentials of the coordinate function. You've probably seen this argued in completely different ways before, right? That the differential of a function is given by the partial derivatives of the function multiplied with the differentials of the coordinate functions. The next slide is just an exercise for you. You don't have to hand that in. It's just a suggestion. Try to calculate how cotangent vectors change their coefficients under change of chart. I mean, you know, of course, what comes out, but it's a nice exercise to see how it comes out. Especially, it only comes out the way you expect if you assume that you use the dual basis. Okay, some notation and terminology. The elements of the tangent vector space are called contravariant vectors. The elements of the cotangent vector space are called covariant vectors. And we will often write symbolically a tangent vector in this way and a cotangent vector in that way, even if we don't specify a chart, just so that we can work with it. It's implied then that, well, just choose a chart, then this will be true. You see, we don't actually have such things on the abstract manifold. We have to go to a chart to have partial derivatives. So we are now ready to define tensors. There are tensors of various ranks where R and S are integers running from 0 to infinity. I mean, it could be any number between 0 and infinity. A tensor T of rank R and S is an element of this vector space here, which is the tensor product just defined. I mean, the tensor product is always defined, as you've seen in quantum mechanics. It's the tensor product of these vector spaces, where you have R tensor copies of the tensor product of R copies of the tangent space and S copies of the cotangent space. in a chart, every tensor has a coefficient matrix like this with S coefficients with lower indices and R coefficients with, of upper indices. For the space of RS tensors, we inherit a basis from the basis of the tangent and cotangent spaces. This is a basis of the tangent space. This is another basis of the tangent space. The tensor products give us a basis as well here with the cotangent spaces and their basis as well. Notice that this doesn't mean that every tensor of rank R is the product of so many tangent vectors and so many cotangent vectors. No, it means that every tensor is a linear combination of products of contravariant and covariant tensors. This is the same math as the math of entanglement in quantum mechanics. If every tensor were just the product of contravariant and covariant vectors, there wouldn't be any entanglement. But there is in general, this thing doesn't factor. It's a linear combination of objects of just one index. But I'm not saying that it has anything to do with quantum mechanical entanglement. It's just the same math, not the same physics. Okay, under a chart change, one can easily show, and you've probably done that in a previous course, that tensors will change their coefficients according to this law here when you change chart. And this is simply inherited from the way that each individual tensor factor changes coefficients. This is all with respect to the basis of the dxi and the d by dxi. If you chose different bases, then the transformation behavior would be different. And as we will later see in this course, in principle, and it can be very useful, that when you change chart, you don't even change bases. If you don't change bases when you change chart, you're not changing the coefficients at all. Okay, but if with a change of chart, you automatically change bases from the partial derivatives with respect to one set of variables to the partial derivatives with respect to the other set of variables, well, then you buy into that transformation law. But if you don't change your basis along with the change of chart, then those coefficients don't change either. Okay, so the physicist definition of what the cotangent vector is and what a tensor is really dependent on choosing always the basis in the tangent vector that comes with the coordinate system. You could choose other bases. Okay, so what we see is that tangent and cotangent vectors are special cases of tensors. The tangent space is simply the space of tensors of rank 1, 0, and the cotangent space is the space of tensors of rank 0, 1. Any questions so far? Because if not, then we can move on from local to global. So far, we've done everything at a point P. Now, let's move to the entire manifold. For every point P, we have a tangent vector space. Of course, also cotangent space and tensor space, but let's start with just a tangent space. So at every point P, we have a tangent space. So we have a pair, a two-object thing, a tuple, which has a point and a tangent space. Let us collect all those tuples. So let's consider the union of all the tuples of a point on the manifold and the tangent space for that point. This is called a tangent bundle. It's the collection of all of them. The points P are called base points. The tangent spaces that are associated with them are called fibers. It turns out that the tangent bundle is itself a manifold. It's a 2 n-dimensional manifold. Why? Well, intuitively, you need n numbers to specify a point, if you use a chart, and you need n more numbers to specify an element in here. So you need 2 n numbers to specify everything. Tm is also then called the total space. So when Tm is a total space, it's a 2 n-dimensional manifold, then what do we call M? M is then called the base space. So you started with the base space, just a manifold, a differentiable manifold, and then you turn it into the tangent bundle by this construction here. Now remember that all of those things that you attach here, all of those tangent spaces are isomorphic to Rn. So they're all just copies of Rn. Therefore, Rn is called the standard fiber for our tangent bundle. We obtain other fiber bundles by using other standard fibers. So for example, if we choose for the standard fiber not the Rn of the tangent spaces, but the Rn of the cotangent spaces, and we get a cotangent bundle. And similarly, we can get the Rs tensor bundle, TRS, by attaching the tensor spaces, which are higher dimensional spaces for every point. There are other fiber bundles as well. In particular, you can choose for your standard fiber, for example, the space in which isospinors live for gauge theory in the standard model of particle physics. These would be vector bundles, usually with a complex vector space attached. So for example, for QCD, you would have a C3, a 3-dimensional complex space attached for the fermions, for the gluons. And then for gauge theories, you also need fibers that are completely different, that are not vector spaces, but for example, groups, like the SU3 for QCD. So you could have that, you start with a base space, which is the manifold, let's say, space-time. And then you associate not a tangent space for every point, but a group element for every point. These would be principal bundles. Now in this, there is an important map, pi, and pi maps from the total space back to the base space. So it maps from, let's say, the tangent bundle to the manifold by forgetting. Basically, the total space, the tangent bundle, knows about points and the tangent space attached to them. This bundle projection, pi, simply forgets everything about the tangent vectors and just gives you back the point P. So it maps a tuple, P, TPM, that's a typical element of our tangent bundle, into just the point P. So that's the bundle projection. The pre-image of pi is the tangent space. Now then, a section sigma of our bundle, for example, the tangent bundle, is a map from the base space into the total space, which is a continuous right inverse of pi. I'll show you in a moment why that makes sense. So, but what does it mean that it is a right inverse? So here you have the bundle projection, which is simply taking an element of this and forgetting the tangent space. And here you have a section. So what does a section do? It's taking a point of the manifold and producing a point of the manifold and a tangent vector. And then the pi will forget the tangent vector again and just produce the point of the manifold. All of this is just a complicated way of saying that sigma is in effect, a section is in effect, I will make this in effect more precise in a moment, is in effect a vector field. See, if you have a vector field and you feed it to the bundle projection, then it will simply forget the vector. it will forget the tangent vector, for example, and will just give you back the point. So every right inverse to the bundle projection is basically saying, okay, for every point of the manifold, you write a vector, and then the bundle projection gets rid of the vector, so you're just left with a point. You see, remember what the graph of a function is. When you have a function f of x or f of a, when you graph it, literally, when you draw the graph of it, if you ask Maple to draw the graph of a function, what does it do? It plots for you the set of pairs of inputs to the function and outputs to the function. Right? So, like the points and then what the function associates to them. So if you give a function or you give the graph of the function, it's the same thing. Right? So a section does just that. The graph of a field, such as a tangent vector field or cotangent vector field, let's say a tangent vector field, the graph of it is such a pair. Points, and then the tangent vectors to that point. And that would be in the total space, in the bundle, in the tangent bundle. And then that's a right inverse to the bundle projection pi, because the bundle projection pi is simply dropping that and gives you back the point. Right? So you've not done anything. The vector field gets you from A to A comma f of A, and then pi undoes that, is a left inverse to that, by just forgetting this part. Okay, so examples. A tangent vector field is then a map, xi. I'm using the same notation as before, but it's a different thing now because it's a vector field. It's defined on all of the manifold. It's a map from points of the manifold into the tangent vector space, and in a chart, it looks like this. It's, again, those directional derivative weight coefficients, but they can now depend on where you are on the manifold. A cotangent vector field is a map from the manifold into the cotangent vector space, or you can look at the graph of it, of course, as we just described, and you get the pair. So the cotangent vector field is such a map. And here we choose the dual basis for the purpose of writing down a cotangent vector field. We know that every cotangent vector is a linear combination of those guys, so definitely every cotangent vector field can be written in this way. And tensor fields, similarly, take this form. They map points in the manifold into elements of the tensor space, the RS tensor space, and in practice it means basis vectors, and then coefficient matrix that depends on where you are in the manifold. Mm-hmm.
For this to make sense, do we need a single chart for the whole manifold?
Yes, yes. I'm always talking about, sorry, I meant, no. Yes, I used a chart to write these things down, but I'm not assuming that one chart suffices for the manifold. You may have to use several charts to cover the manifold completely. But that doesn't change the fact that on every chart it looks like that.
But like, assigning a subscript to each coefficient.
Yeah, actually, I'm getting to that because there's going to be some interesting thing. That's actually the next slide, and we're almost done. You see, why did we bother with fiber bundles? Why didn't we just say, yeah, well, vector fields, tensor fields, cotangent vector fields, and so on? Why bother with this business with the fiber bundles and the bundle projections and sections and so on? Why use that language? What do we actually get from that? It turns out that you don't always have sections. You don't always have vector fields. You don't always have tangent vector fields and things like that. Fiber bundle language is useful to capture the possibility of global non-triviality of your differentiable manifold and the structures that live on them, such as vector bundles and principal bundles with groups and so on. Here's some intuition. We're not going to use this much throughout this course. I will come back once again to this. But, okay, let me first say what it is and then what we'll do with it. So consider M a differentiable manifold that can be covered with two neighborhoods. So let's say the manifold is this ring-like thing, or torus-like thing. Let's think of it as a torus, so that it doesn't matter. It's a ring-like thing. It has a hole in the middle, and let's say you cover it with two neighborhoods, U1 and U2, and they have some overlap there, so that you have a nice atlas. Now, fiber bundles are required to be locally trivial, which means that M is required to be coverable by open sets in such a way that for each open set, we have that the pre-image of the open set is simply the Cartesian product of the open set of the base space of the manifold and Rn. But that doesn't mean that overall the entire fiber bundle is trivial. It doesn't mean that that isomorphism extends to the entire manifold. Fiber bundles are allowed to be globally non-trivial. Namely, for a suitable bundle, you can arrange that, for example, the pre-image of the region U1 is isomorphic to U1 and Rn, and that the pre-image of the region U2 is also isomorphic to U2 and Rn, but the isomorphisms don't have to match here and there. You don't have to match. You can imagine that you have a twist in there, like a Möbius strip. And then that wouldn't work. And then you would have a mismatch of the isomorphisms. Of course, that's not completely bad. It doesn't mean that everything goes wrong. It just means that the isomorphism, it will mismatch up to a linear transformation. Up to a linear transformation, which is an element of the group. Oh, it dropped off the screen here. An element of the group GLN of R, the general linear transformations of Rn. And that would be then called the structure group in this case. This is an important observation because what it indicates is that if we want to study the connectivity properties of differentiable manifolds, this is an avenue to pursue. For example, if the manifolds in question are two-dimensional, if need be, we can just plot them by machine and check for holes and handles and whatever non-trivial structure they might have. But what do you do if the dimension is 27? Then how do you check whether it has holes and tunnels through it and handles and whatever the higher dimensional analog of these structures might be? It's very difficult and can't really do it by machine or by intuition. But what you can do is you can check what kind of bundles can be put on there. For example, does it have sections? And what kind of bundles can be consistently put there under which conditions? And it turns out that there's a whole theory. There's a whole theory built on that. The idea being to map differentiable manifolds onto so-called geometric invariants, which can then tell you whether or not two manifolds are the same or different. Nobody has really succeeded in completely classifying differentiable manifolds in this way. And basically, the invariants that we have are not sufficient, but they're necessary. So if two manifolds have different invariants, you guarantee that they are different manifolds. But if they have the same invariants, they may still differ in something that's not captured by the methods that we have. Anyway, we are not going to do much with this. I will later in the course talk a bit about, I think, K-theory and a little bit of homology, cohomology, but not much, because while this is very important for particle physics and in string theory and areas like that, there is no indication that for space-time we need that. We haven't seen any indications that the universe is like a donut or anything like that. It is in principle possible, but there is no evidence for that fact. But if it turned out that this is the case, this would be the math that we would have to use. Finally, just completing the task of going from local to global. Let us now consider the algebra of C infinity functions from the manifold into the real numbers. We will write that f of m. So we are no longer considering the germs of functions, but the actual functions. We assume them to be differentiable, all of them, as many times differentiable as we need them. And one can show that the contravariant vector fields are the derivations on the algebra of functions on the manifold. What does that mean? It means that the contravariant vector fields are linearly mapping our algebra in a way that respects the Leibniz rule. So we have that if you apply a vector field on the product of two functions, I mean number-valued scalar functions, if you apply a vector field onto the product of two functions, this being a function itself, you can do that, then you obtain the same thing as if you took the vector field, applied it to one function, obtain a number, multiply with the second function, plus take the first function, which is a number-valued thing, multiply with this number-valued output, and there you have it. That's the Leibniz rule. And that's true for all f and g being smooth functions in f of n. Okay, so that was straightforward. And then just a preview for Friday, we will do differential forms. And you've already seen some differential forms. I didn't tell you yet, but now I'm telling you that you've seen some differential forms in this course. In particular, the algebra of smooth functions on the manifold is an algebra of differential forms. It's called lambda 0, and it's called the algebra of zero forms. Also, the set of covariant vector fields, so it's the set of covariant vector valued fields, is denoted lambda 1, and it is called the set of one forms, differential one forms. And then what the differential R forms are, well, we'll get to that in detail. Let me just give an indication. For R equal 2, 3, and so on, the set lambda R of differential R forms will be defined to be the set of totally anti-symmetrized tensors of rank 0R. Now, this may look very artificial. Why those? Why just the covariant ones? Doesn't seem fair to the contravariant ones, right? You could take contravariant tensors and anti-symmetrize them, and then call them the Perimeter Institute differential forms, right? Why don't we do that? But there's something special about the totally anti-symmetrized covariant tensors, and that's their transformation behavior under change of charts. This makes them uniquely qualified for the definition of integrals. Can't use anything else to define integrals but differential forms. Every integration is ultimately the integration of a differential form, and it's the covariant part of it and the antisymmetric part of it that will be essential to get the transformation properties right for integration. Why antisymmetric and so on? Well, it's when you change charts, it's just a preview. When you change charts, then you know that an integral will change its measure. Right? You get this Jacobian factor, the Jacobian determinant. The Jacobian determinant is a determinant, totally antisymmetric. This is what the R forms will achieve. They will achieve that Jacobian factor for us, and that's why they will be so important. Differential forms are the basis for integration. Okay, so that's it for today.